Yes. Okay, so let's finish up this problem. You guys already started. This is the last notes of more implicit differentiation, so please ask questions as we get to them. Okay, first of all, you guys have slept a few times since we've done this, so remember that you're deriving with respect to x. So what's the derivative of the 3x squared term? 6x. Nothing fancy or special about that. Okay, the minus x times y. This is where you need to use product rule. Now you could just go product rule with x times y and then make sure that you distribute the minus. I find it to be a little bit easier if we do something like that, where our terms are negative x and y. Okay, so I'm going to do a plus. Okay, the derivative of negative x would be negative 1 times y, right? Derivative of the first thing times the second thing, plus for product, the first thing, negative x, times the derivative of y would be 1 times dy over dx. Okay, you have to use product rule when you see that x next to the y. Okay, equals, what's the derivative of 8y? 8 times dy over dx. Because again, we are deriving a y term. So notice that we didn't put dy over dx next to each y term. We did it when we took derivative of a y term. Okay, the next thing we had to do was to get all the dy over dx terms on the left, and then to kick everything else to the other side. So I'm going to go ahead and rewrite this big box as negative x times dy over dx. You could definitely keep the parentheses and the 1. It's just not necessary. The 8, I'm going to subtract to the other side, so minus 8 dy over dx. Okay, this 6x, I don't want that, so I'm moving it over to the right, so minus 6x. And then this is a minus y, so when I put it on the other side, it becomes plus y. Okay, the next thing that we did is we would circle the numbers or terms in front of dy over dx, and really that's just designed to help you organize your work here. It's not required, you don't have to do that, but when we factor out dy over dx, circling those things makes it really obvious what's left over. So then my final answer I get when I divide that negative x minus 8. And that's your answer. Okay, so don't forget product rule there. As far as grading wise goes on the quiz, if you make a mistake using product rule, that's small points off. If you don't even do product rule, that's big points off. And obviously it really changes your answer a lot. Okay, let's try the next one. Okay, so I see this x squared plus y squared, the whole thing squared. That makes me think of chain rule. When I derive this left side, I'm going to need to use chain rule. To get out of that, what I could do is actually square this binomial. I could do x squared plus y squared parentheses times parentheses x squared plus y squared. But if I do that, I'm going to get a product rule out of that. Like, because you're going to do x squared times x squared and then x squared times y squared twice. And then y squared times y squared. So I'd really rather not do that. And I want to show you what happens when we leave it alone. But the right side, and again, we don't even have to ever simplify. It's just, it could possibly make your answer easier. So look at the right side. If I leave the 12 where it is now, you might get confused and think, well, do I need to do product rule or chain rule or what? So what's something really easy simplifying that I could do to the right side so that I don't even have to mess with the whole parentheses? I'm just going to distribute the 12. Again, this is not required. I could do this problem without doing this step, but it's actually going to make the next part easier. So when you're looking for, can I simplify or something, the very beginning equation, only do it if you're pretty sure it's going to make the problem easier, because most of the time it's going to make it harder. Okay, So back to the problem. This x squared plus y squared is in parentheses. It's being squared. The squared is the shell of the M&M. The in the parentheses is the chocolate. So I need to move that 2 to the front. I need to leave the x squared plus y squared alone, and I need to decrease the power by 1. So that was me deriving the shell, which was this squared outside the parentheses. Leave the chocolate alone, and now what do I need to do? Times the derivative of the chocolate, which is the x squared plus y squared. Notice I'm using parentheses here because I'm going to write more than just a single term. So derivative of x squared, 2x. Okay, plus derivative of y squared, 2y times dy over dx, because I took derivative of a y term. Okay, on the right side, taking derivative of 12x squared, pretty easy, 24x. Taking derivative of minus 12y squared, what would that be?
Minus 24y.
Yep, minus 24y times dy over dx. Okay, then we get to where we like to box stuff. And boxing this is totally fine, but I have an issue over here on the left side. Do you guys see where my issue is? Okay, if I box this plus 2y times dy over dx, that's not all that's over here. What is happening to everything in these parentheses? It's being multiplied to this. So don't write this down on your paper, but I want to show you something. What if we had something like this? 3x times parentheses y plus z. Don't write this down. Just watch, because I'm going to erase this in just a second. Okay, and I was needing to isolate the y or the z. You might think divide by 3x. That's an option, but it actually is going to prevent more problems next. So if the problem is the parentheses, the fact that this is times something in parentheses, it's the same idea as what we did with the 12, you would want to distribute it, right? And go 3xy plus 3xz. And now you can totally treat each term separately. Okay, do y'all see that? So I have the same thing going on up here. So I'm going to erase all that, and we're going to actually do this with our problem. So if the problem is that you have inside parentheses, you have something you want to keep, and then this little 2x right here, I want to kick to the other side. Well, I'm supposed to be multiplying something, so I am going to take all of this and distribute it to the 2x and distribute it to the 2y dy over dx. And so in the short term, it's going to be a lot of writing, but it's going to make this problem look just like any other problem. Don't worry about simplifying. So there I've distributed it to the 2x, and now I'm going to go plus, and I'm going to distribute it now to the rest. The whole reason we wanted to do this was because I needed to kind of shake things up a bit so I could clearly see which was my dy over dx term and which was not. Okay, beforehand I could not just subtract out that 2x. It's being multiplied to something. Okay, now I can subtract that whole term. Let me go ahead and rewrite the right side, and let's try the box thing again. So this thing was still, we're still just going to rebox that. And now I can box this whole thing as well. And I can do that because it's plus, indicating its own term, 2 times this thing in parentheses, times 2y, times dy over dx. So that's something that I am going to keep on the left side, this box right here in the middle. Yes? When you stop multiplying. So like if after this, the question was, when do I know where to end the box? If it had been plus 3x, I would have to end it before that next plus or minus. And since this was minus 24y dy over dx, I need to add it to the left side. I like the 24x on the right side. I'm going to keep that. And then this whole thing in the front, and remember that was separated by the plus, just to really continue to answer your question. That's why that's separate. I'm going to subtract that. And so it's super long. There's a lot to this problem, but now I can easily see, okay, this thing is being multiplied to dy over dx, and so is plus 24y being multiplied to dy over dx. I'm ready to factor. And you always factor out dy over dx. No one in this class has asked me this, but some people in my other classes have been like, why aren't you factoring out the y as well? That's part of GCF. We're actually not factoring GCF. We're just factoring out dy over dx. So even if you could factor out more, you're not going to. And some of you are like, oh, I never even thought about that. On the right side, we just keep on writing. Once you get a single dy over dx, though, you should feel like accomplished. I mean, really, the last step, dividing, all you got to do is divide over that whole thing. So I'm going to rewrite it as dy over dx equals the whole right side over this part that was left over in the factoring. And this thing could be simplified, but we are not going to focus on that now. So that was definitely a step up from some of the other ones that we did. Okay, any questions on that?
How many word problems were we on?
Okay, so let's practice this, translating the following from English into math. So when we're doing word problems, you're going to read through the word problem, and you have to know, like, mathematically, what does that mean? So on number 1, it says the radius is increasing. Okay, so the radius, r, is increasing at a rate. What does the word rate make you think of that we've been doing? Slope, or what else could we say? A-rock, derivative, I-rock, but derivative, okay? Here's another way we know we're doing a derivative or a rate. See how the units are meters per second? That's how all rates are going to be. They're going to be something per some unit of time. Okay, so this is how you write this in math. You write dr over dt. The d here is for delta. Remember delta, it means change. So it's like the how radius is changing per how time is changing. Okay, which is a lot like slope, derivative, it's all related here. Since this is increasing, we're going to write a positive, in this case 5 meters per second. If we were decreasing, we would write negative 5 meters per second. So when you see rate, you need to be thinking that whole d, in this case r over dt. So then what about 2? The volume of a sphere is decreasing, again with the rate, derivative, 6 cubic feet per minute. That's usual for a rate. So how could I phrase this? So dv, the change in v, over the change in time. These problems don't have to be in relation to time, but they will be. Okay, so if you're like, how do you know it's dt? Well, because of the nature of the problems we're going to do, it's going to be in relationship to time, with respect to time. Okay, and what should this equal if it's decreasing at a rate of 6 cubic feet per minute? -6. And then one thing I want to point your attention to as well is that, see how V is on the top part of the left and we have cubic feet? That's always going to happen. T, time. So your units should always match up with what you write. Okay, what about 3? Determine how fast the height is changing. They did not say rate, but they implied it with this word changing. So how could we phrase that? So let me tell you, it's going to be d something over dt. D what? For height, we could probably use h. And then I'm going to put question mark because it says determine. I'm not asking you for today to solve any of this. We're just practicing the notation. Okay, and then I threw 4 in because I want to, some students, they get so caught up on the new stuff, they make everything difficult. Okay, and that happens a lot. See how it just says radius is 6 meters? That is not a rate. We can tell by the units and the fact that they don't even say anything about rate. This is just r equals 6 centimeters. So sometimes it'll be r, sometimes it'll be dr over dt. And when we get into the problems tomorrow, it'll make more sense. But you got to be able to translate that over. Okay, what I would like for you guys to do is 5, 6, and 7 on your own. You're going backwards. You're writing something out. Okay, so what do you guys think about my answers here? Did you guys use the words increasing and decreasing? Okay. The units there helped us know that it was a rate. Okay, same thing on 7. The units were not cubic feet per anything, per second, per minute or anything. And so that was just a regular volume. Okay, so number 8 says dc over dt equals 0 millimeters per second, where c is the hypotenuse of a right triangle. Okay, so here we have a right triangle. Here's c. And c, what's happening to c? Is it increasing? Is it decreasing? What? It's not changing. So the most simple way to put this, I think, is just to say the hypotenuse is not changing. How many of you have ever like strung up Christmas lights or cleaned out leaves from the gutter or something where you needed to get to the top of your house? Okay, what did you use to get up that high? A ladder. So imagine that you prop a ladder up against a house and you really don't secure the base of the ladder. What's going to happen to that ladder? It's going to slide down. Is the ladder, which is the hypotenuse, changing height? Is it getting shorter or taller? No. Everything else in the problem is changing, but the hypotenuse would not be changing. Ladder problems are real classic related rates, and we'll see some of those this week. Okay, let's talk about 9 through 13. Go ahead and write down all the formulas that you can remember. I know that you don't remember all of these. That's okay. But the ones that you can remember, go ahead and write down. Okay, let's go over what you got. What is the area of a circle?
Pi r squared.
Pi r squared. You should know this formula. You're expected to know it. What is circumference? 2 pi r or pi d. 2 pi r is going to be more useful for what we're going to do. Real quick, what is the derivative of pi r squared? 2 pi r. Whoa. Not a coincidence. Okay. Volume of a sphere. Anybody know this one?
Pi r squared.
Wait, I heard a cubed, which was right.
Isn't it s cubed?
You're pretty close. It's 4/3 pi r cubed. 4/3 pi r cubed. That's the volume of a sphere. Probably didn't remember this one. On the AP test, I've seen this given, and on other materials, I've seen it where you were expected to know it. We're going to do enough sphere problems to where you're probably going to know this formula. And we're going to apply the same thing. Remember how derivative of area was circumference because it was like a 2-dimensional, then a 1-dimensional? Well, volume is 3-dimensional and surface area is 2-dimensional, so we can apply the whole derivative thing. What would you get when you do 3 times 4/3?
4.
Just 4. pi r squared. That's it. That's surface area of a sphere. Okay, Pythagorean Theorem. Hopefully you know this. I find that students, even students who forget everything, tend to remember this. Okay, what about area of a triangle? Okay, so the way I'm going to write it for our purposes is 1/2 base times height, because what happens in derivative land when we have a fraction, or like an all over 2? We start thinking quotient rule. And really, you don't want to use quotient rule if you don't have to. So we're just going to do 1/2 base times height. That's still going to be product rule, but it won't be that bad. And then volume of a cone. Anyone know it? 1/3. So it's 1/3 volume of a cylinder. So what would a cylinder be? A circular base, pi r squared times height. So a cone is just 1/3 of that. Okay, it's 1/3 of a cylinder. Okay, when is a circumstance? I never feel like I really write this the correct way, how you're supposed to, but when could you have a rate being 0? We already talked about one thing. Do y'all remember?
The ladder.
The ladder. Okay, unless you have an extendable ladder, it's not changing. And we won't do extendable ladder problems, so that's good. Can you think of any other time when a rate is 0, where maybe something's getting bigger or smaller, but only certain dimensions, and other dimensions aren't getting bigger or smaller? They're remaining unchanged.
Faster, but it doesn't get bigger.
Wait, what did y'all said something at the same time?
Slide.
So a slide, so don't think velocity so much as like,
A flagpole.
okay, so what's changing on a flagpole? The shadow. Okay, but what's not changing? The height of the flagpole. Also, we have things like, think about a pool that is like an above ground pool that's a cylinder, and we were filling it up with water, or let's say the water was leaking out. The height of the water is changing, but what about the radius? It would be the same, because it would take on the shape of the pool. So there are a lot of situations where there is a rate of change that's 0, whereas there's other rates of change that are not 0. Okay, how do we use the units? How do the units help you to know when the expression is a rate? Yep, it's going to be something per time. Second, minute, hour, day, whatever it may be. An idea